Okay. Since last week when we met, has anyone bothered to figure out what is a transformer? Okay, let me put it this way rather than asking you this question. In one line or two lines, if I ask you what is a transformer, or somebody in the interview panel asks you what is a transformer, what will you say? I hope nobody will say it's an electrical transformer which converts DC to AC or something like that. No, that is also correct. But what would you say when I ask you what is a transformer? Will you just say it's an LLM? Or will you say it is something else? Okay. I think at this stage, let's not answer that question. Let's see whether you can give a better answer at the end. Now, see, perhaps, I don't need to say this, perhaps the whole future of computer science rests on the existence of transformers. I won't be too far off the mark when I say that, because the whole of Gen AI is taking over the world, and Gen AI starts with this concept of transformer. Now you have been, I am sure, using transformers for quite some time. I at least hope you have been using transformers. You have been using ChatGPT, so you have been using some kind of transformer. But what we are going to try and understand is the anatomy of a transformer. Why do you create a transformer? Well, you will not perhaps create a transformer in your life because it's already done, but you will definitely adapt transformer for vision tasks, for video tasks, for many other things. Transformers perhaps will be your livelihood. In fact, if you end up doing anything worthwhile in the next 4 years, it will be around transformers. That's for sure. If you find yourself in the next 2 years not doing transformer stuff, I would say that your career is not taking a very rosy path. So it's as important. I mean, one way to define success is by the currency pocket that you have, currency that you have in your pocket. The other way to define success in computer science is how deep and how well do you understand transformers. I'm making it very simple. The road to wealth starts with transformers. Now you'll say, if transformer is already done, why do I need to learn transformer, and why are you saying it makes so much money? Well, transformer, we have just touched the tip of the iceberg as of now. There is a whole domain which many people don't see, which is of hyper customization, which transformers is going to start. What is hyper customization? I think I have given you the analogy. Today, your shirt and your shirt, you both buy from a same shop or whatever. It's not customized to you. Your food is not customized to you. Your medicine is not customized. Your education is not customized. Whereas, so far if you see, evolution of world society has been to do what is called one size fits all. What do you mean by one size fits all? I design a solution, now you adapt to that solution, you use that solution. Was the solution created for you as a person in mind? No. Very little. The food you eat, the clothes you wear, the medicine you take, the education that you receive, I'm just touching some basic things, is not tailor-made for you. It was never tailor-made for you. It is somebody designed it and then you adapted to it, which is loss of efficiency and loss of things. Now this in itself is what transformer is going to enable, if you know how to use transformers well, that they will enable a world of hyper customization, whether it applies to food, medicine or anything, and how they will do it, you will figure out, or maybe the problem is not solved yet, but that is where the problem is going to get solved. So what I am going to do is I am going to assume that you don't know much about transformers. So first, what is important is the conceptual understanding of transformer, which is derived from that paper. Attention is all you need. Now that reminds me, I had asked you to read that paper. Anybody read? It's in English. Oh, very good. Now can you raise your hands again? 1, 2, 3. Good. Nobody here? 4, 5, 6, 7. Good. Now about 10 people, I guess. In order to appreciate that paper, you also need to understand the code behind that paper. So we will try and look at the code, but that all depends on you, how fast you take in the initial ideas. Okay. Now, I am going to start very small. The book I am referring to is Large Language Models, hands-on large language models. The heading is over there. Hands-on large language model. This is a beautiful book by a person who is very good. His name is J. Alamar. He also has videos. He also has other things. But this is probably one of the best books which has come out recently, which does a good treatment of transformers at the basic level. There are other books also, but I have seen this book does probably one of the best jobs. Initially, he used to write blogs and create GitHub. Now he has whatever he used to write in his blog, I think somebody has worked on it and converted it into a book. So this is that book, and very, very lucidly explained. Okay, so let me use his presentation itself to explain what is a transformer. Now I am going to go inside the transformer, but I will start with the outside. Okay, so I hope this is this legible? Is this clear? No, not the English entirely. If you can come little closer, maybe things become. Okay, let me see whether. Okay, I'll read out as I go. So there is a prompt which is given to the LLM. Write an email apologizing to Sarah for the tragic gardening mishap. Explain how it happened. It's not important what the message is. And the transformer LLM is supposed to produce some text in response to that question, which is what your ChatGPT does. So we are going to understand how that happens. But this is what a very, very high level abstraction of a transformer LLM is, that given a text prompt, it generates an output in response to that text prompt. That is what it does. Now, how it does is obviously interesting. This doesn't work. Okay, so here is one idea which is important. So if you see the transformer LLM and you see this, if you see this slide, just the left hand side, or okay, left hand side. Let's ask the people who are read that paper. What does this? If I were to capture that diagram, the left hand side diagram, in a sentence or in a phrase, what phrase should come to you? People who have read the paper, then I'll describe. If I show you this slide, show you the left hand side alone and ask you, there is something shown there. Now obviously you are not reading it. What does it depict? What concept does it depict? Yes? Multi-headed attention. No, that doesn't depict multi-headed attention. What does this depict for people who have read the paper? Yeah? It depicts something very significant about the paper. Okay. So, what it depicts, I'll talk about this term. It's a very simple concept. It depicts what is called in transformers as what is called auto-regressive generation. Now, let's understand what this means. Auto-regressive generation. the way it is proceeding to generate, first the sentence was given, and what did the transformer do? It generated one word called dear. After that, what did it do? It used the rest of the sentence and dear and generated the next word, which was Sarah. Then it used dear, Sarah and the rest of the sentence. Obviously, it lost the first two words and produced another word called comma. It didn't produce a word, it produced a comma. And after that, it took all that and produced a new line. So, step by step, using what is called as the context. So, the one which is shown in the black, that is called the context. Context means what is required to generate. That is called the context. So, using that context, it generates the first word. And using the first word and the rest of the context, it generates the next word. And using these two words and the context, it generates the third word. In this case, the third is not a word, it's a comma, whatever it may be. And then using the three and the context, it generates the fourth. So, this is how any LLM proceeds. It is word by word, it is proceeding. So, it is taking the context, producing first and then going. That's why it is called auto. Why is it called auto? Because it is using what it has generated. It is eating what it has produced and generating the next word. A lot of people call it the self-synthesizing machine. So, basically it is synthesizing from what it itself has generated and using it to synthesize further. So, this is where the smartness of an LLM starts coming, that it is not dependent on anything. It is using itself, creating the first word and producing. This is called autoregressive. So, there in the next place he spells it out. He says output token, and output token is appended to the prompt. Then this new text is presented and to the model again for another forward pass to generate the next token. So, every time it is doing a forward pass and generating one token after another. Why just one token? But the speed at which it is generating the tokens obviously is so fast that you are getting spewing out sentence after sentence. That is what is happening. We don't feel the speed. So, next. Next. Oh, wait. So, the way I would do it, I'm not going into the code, I'm still looking at it at black box level. Look at the blue thing. That is a prompt which says how it happened. I give the prompt and give it to the generator. Now, I don't know what the generator is, but the generator generates an output. Now, if I ask for printing output 0 generated text, next page, it generates this text. This is the output text. Now, you see it has generated a pretty good text out of the LLM. Now, it has stopped at a particular point. The reason it stopped is very simple, because I didn't show you that. While generating, I had asked for a maximum limit. So, it stopped at maximum limit. Typically, this maximum limit is dependent on what context size you would want it to finally generate. Often, our ChatGPT 4 used to stop at 2K. It used to generate 2K tokens and stop. Nowadays, it generates 4K tokens. Nowadays, it generates 8K tokens. It's going to go on. So, as the machines are becoming more powerful, it is not limiting itself to a small generation. It is generating bigger. And this story will continue till the point that today people are producing novels simply by writing a nice prompt and extending the context. You can produce a novel. So, anybody who writes novels is obviously out of job. Okay, next. Now, we are getting into, we'll slowly start getting into this way of generation. How does this mechanism of generation progress? So, now I am going to give you a first level view. This book progresses very nicely into deeper and deeper. So, right now, if you just look at what is that transformer consisting of? Well, at the core, not at the core, at the start, it starts with what is called as a tokenizer. Okay. Now, let us talk about tokenizer a little bit. Now, tokenizers have been in business for almost now, the first good tokenizers start coming into the market in 2012, 2013. So they are pretty old. They are about now 10 years old. Tokenizer, what is a tokenizer? It converts every English language or any language, breaks it up, chops it up, and yields what are called tokens. Tokens are basically numbers which identify the portions of the word. Now, generally, there is no one-to-one correspondence between a token and a word. Often, words like together get split into two and gather, or I mean, there are many words. I can give many examples, but that's not important. Most of the words split into at most two tokens. To give you an average, now why tokens are important, I'll tell you. But 1,000 tokens, 1,000 words will end up becoming about 1,500 tokens, to give you a basic maths, because a lot of words in English are actually two words. So they are broken up at the tokenization level into two tokens, not one. So general average we take is 2 by 3 or 1.5. So if you say I have 1,000 words, then ask how many tokens are generated out of 1,000 words, probably the answer will be 1,500 tokens will be generated. Now, why are these tokens important? Token is the unit of operation for the LLM. We'll take it forward, but the LLM never works on words. It works on tokens because they are small pieces of words which we get used. There is another reason why we should know how tokens are, because the monetization of LLM happens on tokens. So when you say how much is this LLM costing, it will say so much per token or per million tokens. So the unit of measurement of traffic for an LLM for costing is based on how much tokens, not on how many words. So when it says I have generated 1,000 words, that is not the pricing unit. How many tokens I have generated is the pricing unit. And general correspondence is 2 by 3, 1.5, but somewhere in that range. So there is a tokenizer. So first step in any, I'll go in more detail. First step in any language generation is you take the prompt, you chop it up, you make it tokenized. After you have chopped it up, you get a series of tokens. Now what do you do after the tokens? What do you do after tokenization? Embedding. Very good. So the next step is called embedding. What is embedding? Basically converting tokens into some kind of a vector space. Now this is where you need to understand. Okay, just pause because it's not as simple as that. Think a little with me. See, a token is just a number. Number, even an embedded version of a token is also a number, but there is a difference. So what we do is when we say a word is there, or rather we forget talking about words, we talk about tokens. So when we say a token is there, I have to take the token and transform it into another high dimensionality space, because I have to start analyzing the token now. And that process is called embedding. So typically the size of embedding will be 1024 bits or even longer, 1024 integers or 1024 bits. It depends on what kind of model size you use. As time is passing, the model sizes are becoming bigger. This is called model size or dimensionality. So dimensionality means I have decided to break this token into how many dimensions. Think of dimensions as, you know, when you think of X, Y, Z, you think 3 dimensions. Imagine that there are 1024 dimensions in which the word has to make sense, or 8192 dimensions in which the word has to make sense. So unless you are able to convert the word into a very high dimensional space, the word stops making sense, or the word will not make sense to you in all its meaning. See, there are many manifestations of a word. A word has a meaning is one part. Is it masculine or feminine is another part. Is it a part of noun is another part. These are very common dimensions which you and I know. Now, in the world of language, computational linguistics as we call it, in the world of computational linguistics, a word has much more impact and much more ability of analysis, We just don't say it's a noun, it's an adverb, or it's a, this kind of a phrase or that kind of a phrase. We look at it from a very multi-dimensional view. The number of dimensions could be 10, 24, 8, 1, 9, 2. So the job of the embedding layer is to take the token and convert this into a huge multi-dimensional space. Imagine a vector space with so many dimensions. Why? Because the word has so many colors, and all the colors of that word have to come out. Now, a lot of work has been done in embedding. Now, embedding did not come as a consequence of this paper. As a consequence of attention is all you need. Embedding is again 2013, and embedding came again from Google, as I told you I think last time, with Word2Vec. That was the seminal paper, again written by Google, which understood how to convert a word into its vector representation. In fact, the word Word2Vec says more things than the word embedding, because Word2Vec says I take a word and just blow it up into n number of dimensions, into many dimensions. Why do I blow it up? So that I can visualize the hidden meaning of this word. Now, hidden meaning, don't take it in a very common sense of what is the meaning of this word. No, there are many dimensions of this word. How is it used? Where is it used? All those things of a word. So just blow it up into a multi-dimensional space. That is what we do. So that is a job of the tokenizer. What is not shown is, or what is implied here is, the tokenizer actually is two steps: the tokenization process and the embedding space. Embedding is this converting into multi-dimensional space. And then we have n number of transformer blocks. Original architecture started with 6 transformer blocks. Today we have 96. 96 is 3.5. I think 4 has around 128 or 128, I think. 4.0 obviously has more. 4.0 actually we don't know. Nobody announced how many are there. Now people are reluctant to share their internal architecture. Till 3.5 people were very open with the sharing. But there are as many, how many transformer blocks you can have depends on how much money you have, because each transformer block is going to take a lot of GPU power, lot of processing power, all of that. So more the number of blocks, more complex the network, more deeper your understanding, and because it's often reported that genuine understanding starts of some things at the 90th layer of a 96 layer stack. Certain things start making sense only at the 90th layer. So you need to put that many layers in, and obviously you need to have the cost. So, and at the end of the transformer block, there is a language model head which can do many things. It depends on how you want to do your encoding. It depends, do you want to generate another word out of it? Or do you want to generate a sentiment out of this whole English? Or do you want to, as you just saw, generate a next word? What do you want to do? It depends on what kind of job you want this encoder to do or this transformer to do. The magic is in the LM head. So the job of the LM head is to give meaning to the interpretation. And when this goes through a lot of learning, it finally learns. So LM head stands for language model head, which can be taken and replaced. And most often in computer science, when you and I sit down to design transformers, we don't touch a whole lot of the transformer. We touch the last part, which is the LM head. It is like, to give you the analogy, to make the transformer do something different, till the transformer block produces something, we keep it same, and at the last level, at the LM head level, it's like changing the cap. You take this cap, put it aside, wear another cap, and your transformer starts doing something else. So it depends on how you train it, and lot of work we do where we don't touch rest of the transformer, we just tweak the LM head a bit and it starts doing something else for us. So it starts performing what earlier was doing named entity recognition, now starts doing generation of new text, or what earlier was doing sentiment analysis of the prompt, now starts doing, let's say, NER. So it can do many things, and it can be made to do many things by removing that head and retraining with a different outcome. So that's pretty smart thing to do. Now this is only half of the transformer. There is another half of the transformer which we call the decoder. This is only the encoder version. Normally what I do is, in order to teach, I first teach only the encoder, because the decoder in many ways is very similar to the encoder with certain restrictions. If you understand the encoder, I can normally bet that you will understand how to write the decoder also. So we will focus on the encoder, but where does the decoder come in? The decoder comes in when you have to translate from one language to another, because as you are generating words, you have to see and watch the translation also, whether the translation is following what you are generating. So if you have to do that, we need a decoder also. But let's skip the decoder for a moment. Let's say we are only doing language generation. The task that you just saw, which is generating a next test, does not need a decoder, because you are not converting it into something else. You are just generating a next token, and for that an encoder is enough. And very often computer science folks have to decide which part of the overall network to take. Do I take the encoder only? Sometimes you would like to take the decoder only, or just take small part of the encoder and a whole lot part of the decoder. You can make it up, make your own transformer out of that. Okay, but fundamentally we need to now get into and understand what happens in the transformer. Now here things start getting a little, no, not so much. Now pay close attention. This brings out the embedding and the tokenizer, more or less what I just said. Now if you see the tokenizer, let's spend a little time on tokenizer and understand embedding. See here in this example, he is assuming a vocabulary of 50,000 words. That is, he is assuming a dictionary which consists of 50,000 words. I mean, that's just an example. I know English dictionary is far bigger, but for us 50,000 is good enough. So first, what does a tokenizer do? Break up the words into tokens, and each token, so not even 50,000 words, sorry, it is 50,000 tokens. So break up words into tokens and give some number, fixed number to that token. Done? That is tokenization. That is converting a word into token and giving that token some fixed number based on what word it is, based on your dictionary. Then there is a portion called embedding, where we convert that token ID into a vector. Now that size, are you seeing a vector next to that token? The below diagram, right hand side below. Are you seeing a vector? There is a vector corresponding to token 0, there is a vector corresponding to token 1, and so on up to token 50,000 or whatever the number may. So now that vector size is what I was talking about. The bigger the vector, the more elaborate is your language description. So I told you typically that vector is 1024, 8192 or even more. Even 8192 I think is what 4 uses. I think 40 has even bigger. So imagine a vector of 8192 there. So that should give you an understanding how the vector looks. Now this is called word to vec. I mean the whole process is called word to vec, where we have converted the word into a vector. Each word gets converted into 1 or 2 vectors, because word may consist of more than one token. Each token will become a vector. Is everybody so far with me? Yes, no? Clear? Okay. Okay. Now let's go to the right. Okay, let's struggle with this. I just want to show you the token probability. I am now focusing on the output. That's why I am showing this important. See, the output is also a token in language generation. Not always. If it is a named entity representation, it is only what kind of entity it is. If it is a sentiment analysis problem, it is what kind of sentiment. But when you are generating new words, you are generating sentences, the LLM task, the output is also a token. Okay, can you see that? The output coming from the LM head also is a token. What is this token? The next possible token which has to be generated based on what tokens have come and what the transformer thinks should be the next word or the next token. So that is the next token. Now, how is this token represented? If you see that token ID represents, okay. Now, actually the output will not be a single token, but think with me, it will be a probability distribution. I am repeating again, the output of the LLM, like we get a word, so we think it's a word or a token. No, it's a probability distribution. What does that probability distribution tell me? It tells me what is the probability of each word in the vocabulary to be the next word in this context. I'll repeat again. The output of a LLM is a probability distribution. The probability distribution tells me what? It tells me how probable each token is in the output. So, what you are seeing there is one of the tokens has a probability of 0.01%. Another token has a next word, because any word of the 50,000 words could be the next word. What is the probability of each word as a next word? So it is starting, what numbers given there are. Some words have 0.01 probability, sometimes even lesser. But the word dear, if you notice, or the token corresponding to the word dear has a probability of 40%. So what does the system do now? What does the LLM head do? First it generates the probability distribution and then it takes the next word and says dear, because that word as per the probability distribution happens to be the most probable next token. That is the decision making. So tokenization happens here and decoding happens at the output. So the decoding process of the output is get the probability distribution generated by the transformer, figure out who is the most probable and give that. Sometimes, okay, now here is the sometimes. Sometimes when you want your LLM to be more explorative, to be more creative, that is a euphemism for hallucination, but let me say that. So you want your LLM to be more creative, then what do? You don't choose one path, dear. You choose the next 4 probable tokens or the next 5 probable tokens and allow that to generate their own stories. That is how you get multiple stories. No, yes. Am I reaching you? See, if I have to generate not one consequence, I have to generate many possible alternatives. What do? I don't take just the most probable. I take the most probable, I take one earlier than that, meaning lower than that, take some 3, 4. And once I take those 3, 4 and allow them to progress by saying, with this let's see what is the next word, and with this let's see what is the next word, then I get variety in my output. That is how I generate multiple different kinds of outputs. That is called, in computer science we call it beaming. So we say I want 5 beams or I want 1 beam. 1 beam means I only want one output. 5 beams means give me 5 different possibilities. At every point generate, anyway it is generating probabilities, but explore 5 paths so you get more creative. Sometimes it's also controlled by the temperature of your transformer. Okay, so that's crucial. This is what I am describing. I have not described what is happening inside. We'll come to that. But what comes at the output is this. Are we clear? So I have described what goes in and what goes out. I'll summarize. What goes in is vectors of tokens. Yes? For every word there is a vector. For every word there are tokens. Tokens become vectors. That goes in. What comes out is probability distribution of the vocabulary, which indicates how probable is the next word, and pick the highest of that normally or more. Correct? So if that is clear, we are ready to move to the next. Yes? This is what input, this is what is the output, and how does it go about? How does it do that magic? Okay? Okay. Okay, this is what we just did. Okay, now this is what we just saw. Okay, now I'll just go through the code here. not code, the pseudo code here. Then we'll look at what is each transformer block doing and how is it doing. This is relevant at this stage. Okay, suppose the prompt is the capital of France is, this is a prompt, okay, and then how does it start? So he is showing you how it happens internally. Again, this is English, this is not how it really happens, but something like this happens. So first is the tokenizer. So it tokenizes the prompt and returns a tensor as a bunch of input IDs. So that is a tokenizer giving you the prompt. So you invoke the tokenizer on the prompt, it chopped it up, gave me the tokens. Then I took the tokens and transferred them for embedding to CUDA, because embedding is a translation into multi-dimensional space. It won't work well on a CPU. So far my code runs on a CPU. Now I transfer that code to the GPU, that is CUDA, and say now I'm handing over to the GPU because GPU will do the embedding. Okay. So my tokenized tokens have gone to GPU. Let's see what happens next. Now, okay, he has not shown the embedding step, but that's okay. Okay, now the model output, this input IDs have to be converted into their embeddings. He has skipped that step, which is okay. And then that is given to the model, the input IDs are given to the model, then model output is taken and the model output. So now I am taking the model, I am accessing the LM head of the model. The model has consumed all the input IDs. The LM head of the model is now, I am asking the LM head to give model output 0, which is what? The first word. Rather it's probabilities of the first word. Okay. Okay. Now, so at this stage, I will have output 0. You see the next operation which is taken. So I have got the probabilities of the first word. Now you look at the right hand side, token ID is equal to, this is the output token, LM head output 0, 0 minus 1 takes the last word in the sentence, and then it does an arg, that gives the probabilities, and then does an argmax. Argmax, you will recollect, gives you the maximum, because I am looking for the maximum probability, and minus 1 for that means the last maximum probability, right? It organizes probabilities in a maximum way, and I am picking the last maximum probability. That token ID I am decoding and giving the output. That is how the output is getting generated. So the only point I am making is what I just said. It generates a bunch of probabilities. You take the maximum of that probability. Here he is taking maximum. You can choose to take argmax up to minus 5 also. So you can take minus 1, minus 2, minus 3, minus 4, minus 5. You will have the top 5 probable words which should come, and then take each one of them and generate that as an output and follow auto regression later. Okay. So anyway, this was, in this case, it turns out that the word which is generated is Paris. Remember the question prompt was the capital of France is, and it apparently, because of its great learning and knowledge and how it did, will come to, generated the word with the highest probability after this happens to be Paris. So it got Paris. So that's why it gave Paris. Okay. Now we are going hopefully into the processing. Next. Yeah. Okay. So now before we get into the token, now there are a couple of points which you need to understand here, and that this is where probably the strength of transformer comes. But before that, just get a hang of it. Now I have the tokenizer there, and I have the sentence which is given, okay, the prompt which is given, and now in older models, okay, here is just doing a recollection before starting the concept in what is the beauty or what is the power of a transformer here. See, it is not that language processing started with transformers. Who used to process language? Which kind of network was used to process language? Very good. RNN, the recurrent neural network. So, the problem with recurrent neural networks was, it was a sequential network. What it used to do is, okay, let's just talk about it for a minute. Suppose it was given a similar sentence and asked to generate a next word, what it would do? It would take the first word, then it would build some state, then take the second word and use that second word to enhance this state, and as each word would come in, it would go on enhancing its hidden state, and at the end, when the time came to predict this big hidden state which it has accumulated, how did it create this hidden state? By looking at each of the words in the sentence, it learned from something from each and every word, accumulated that knowledge, abstracted into a composite hidden state, and used this composite hidden state to predict the next word. That is how an old style RNN would do. Now, and when doing that, there are two problems, which is why the industry discarded RNNs and adopted the transformer model. What are the two problems with that? The two problems with that are, each word is processed one at a time. So, in 1 unit of time, I am processing only one word, then taking that word and going to the next word and enhancing the knowledge of the second word in conjunction with the first word. So, I should have processed the first word and use the second word to enhance the knowledge of the first word. You are getting what I am saying? So, it has to be done sequentially. It has to go one word after another word after another word. That is why the word recurrent neural network, correct? Whether you implement it using a LSTM or a GRU, that is besides the point, they do the same thing. Only thing, the way they learn is different. That is one problem. That if I have a sentence which is, let's say, 1,000 words, and I am asking you to generate the 1,001st word, what it will have to do? It will have to go through each word and produce the next word. It would have the next hidden state would depend on all these 1,000 words, one after another, in a recurrent way. One problem. Second is, it doesn't lend itself to parallel execution. See, I am processing how many words? Only one at a time. No, yes. If you imagine the recurrent neural network, I am processing one word. Yes, while processing that one word, I am taking the hidden state of the previous word. But at one point, I am handling only one word. That is very important to understand. The power of transformer comes because A, it now doesn't wait for each word to be accumulated and abstracted into a hidden state. No, it processes the complete sentence by itself. Yes, that's why there is a restriction on the context size, which I told you can be 8192, can be bigger, or I'm not talking about model size. I'm saying the number of tokens which it can process also is limited. So that limitation exists, but that limitation is far better than going one by one. That is one problem, and there is no sequential processing. This diagram reflects that every word in the sentence is processed parallelly, concurrently, and simultaneously. And that is where GPUs have given it power. It is not one word at a time. It is all words in the context, all words in the sentence. So if my prompt consisted of 1,000 words, all the 1,000 words will be processed one together, whatever be the size of the context. I mean, that would be a limitation of the model, but up to that, all of that will be processed at one go. And that's enormous power as compared to an RNN or an earlier neural network. Did you get that? Because as a young person, you will often ask this question, various interviews, or for yourself itself. Why is a RNN thrown out and transformers brought in? Answer is very simple. RNNs are capable of only sequential processing. These guys do everything in parallel, and how they do will come to in a moment. So I hope these two things are understood. So it does not depend on one by one, and it is not one hidden state. It is many hidden states which together are getting. That's where the beauty of attention comes. Okay, next. Okay. Now, this is again elucidating the same thing again. It shows the same thing but in a slightly different way, and it shows another very important idea. So these are ideas which come together. Again, I am not gone inside the transformer yet. I am just still outside. Now see what is happening. The tokenizer converts these words into tokens, then converts them into embeddings. Can you see the embeddings? No, yes, at the top. Those vectors, they are called embeddings of the tokens. So your prompt is converted into tokens, tokens are converted into embeddings. Embeddings are processed simultaneously. All the embeddings are consumed at one shot. Now you can see the output vectors coming from the transformer engine. Can you see the output vectors? Yes. Now the output vectors which are emerging from the transformer, if you notice something very, I don't know how many of you have that eye, there is something very peculiar at the output side. Do you understand what's happening? Beautiful. You see, the output is producing so many tokens. For each token, it is producing one output vector. But if you notice, the LM head is not showing interest in any of the earlier 5 tokens. It is consumed by only the last token. I mean, it's showing interest only in the last output vector, sorry. No, yes, did you notice? It has ignored the first 5 vectors. It said, I am not interested in them. I am only interested in the last one. So, somehow, during this processing, what must have happened? This last guy has gathered substantial information about the rest of the tokens, about the context of the language. Everything has been absorbed into that one bright last token. That last token has encapsulated the whole meaning of the prompt and its complete understanding. It has all been somehow captured by the mechanism of the transformer into that last token, sorry, the last vector. And it is this last vector which is getting processed by the LM head, which produces the result token, which obviously has to be converted and decoded into whatever based on probabilities and all of that. So the thing which is taken into consideration, if you notice, is just the last token. This is very important to understand. I have forgotten everything, but the transformer mechanism has made that last token learn everything that is to know about this sentence and everything that is needed to generate the next word. It doesn't need anything more. Yes, this is also a very important salient feature of the transformer. Again, I am outside still. I am not entered the den. Okay, clear? Yes, no? Everybody is clear? Simple, no? Okay. So, next. I am not going to talk about the shapes and all that. Okay. Okay. Now, okay, before we enter transformer, one more thing. This is an optimization which was carried out later, not in the first generation, not the 2017 paper, but this happened a little later in 2020, I think. Somebody understood something very smart. Now, I am hoping you will understand this with me. Okay. Now, see, I just made a statement that the last token is all that matters, or the last vector is all that matters to continue the story. Okay. Now, I take the last token or last vector, convert it into a token, and once I do that, that is de-embed it, I convert it into a word, and that becomes my last word of my sentence, right? And now what do? I take the entire context plus this new word, give it as input, yes, no, to the transformer again and ask it to generate the next word, that is the second word. Are you with me? But while doing that, whatever work the transformer has done for the earlier words can be reused. I am talking about conceptually. See, in the first instance what happened? Let us presume there were 10 words. Okay? Those 10 words were processed. And based on that 10th word, the 11th word was generated. Yes? Now, the next time what do I have to do? If my context is exceeded, if it is exceeded, if my context is only 10, then the words 2 to 9 or 2 to 10 and the 11 will be taken. If my context is not exceeded, all the 11 words will be taken. Agreed? But if you now think the difference between the processing which happens the second time and what happened the first time, out of the 11 words which I gave next time, the first 10 words are same if there are 11. Yes, no. Only the 11th word is new. So the processing has to happen only for the 11th word, and later some amount of processing and all that has to happen. But a lot of the processing, a lot, not all obviously, because this new word also has to understand all that. So a lot of the processing which has happened on the earlier 10 words can still be used while generating the 12th word. Agreed? So that principle is called smart caching. So there is a caching concept which is employed. So you see there top, now the word deer is taken. Can you see the word deer? That was generated in the previous iteration. Please look at it carefully. There is that word deer marked in red. All of you are not colorblind, right? So there is deer, which is new generated word. That is taken along with the rest of the sentence depending on context. And do you notice only that last word needs processing? The remaining 10 words already processed, earlier words already processed. So the amount of processing, not just one, there is some more, because this word also has to learn a lot of vectors from the other earlier ones, but to a large extent processing gets conserved. So this was called key value caching. I'll talk why it is called key value caching, but this became a very good technique. The first guys who implemented it actually were Llama 1. The first Llama 1, which again was done by Google, not by OpenAI. They said, you know, we could somehow cannibalize what we have learned in the previous case and incorporate it. And if one day you are ready and you are mature or you are smart enough, we will talk about actually how this is done. It's very interesting how this caching is done. It's a very elegant, very, very crisp technique how this is all done. Okay, it's a very smart way of doing it. Anyway, as long as you get a gist of what is happening, it's fine. We move ahead. Next. We have still not entered the transformer. Okay. Yeah, I think we can skip this. This is the same thing which is being talked about. Okay. Yeah. Okay. Now we will start blowing up what happens inside the transformer and how does it go about doing it. Let's now enter into the inside of a transformer block. So, okay. Now there are in every well, here he is just showing a chain. Tokenizer tokenizes, embedding goes to transformer block 1. What he is showing is every transformer stage generates its own vectors of the same size. Acha, one important thing about a transformer is the model size or the vector size which is there remains fixed. Once right at the beginning, when the tokenizer or the embedder has converted the tokens into those vectors just learn. They don't change their sizes. They remain at that size only, and therefore why that size is kept same, There is also a paper on this to reduce the amount of matrix multiplication cost. So it proves that if you keep them fixed, you save a lot in terms of cost. Anyway, so this only shows that, and then the output vector, the last output vector, is used to generate the output by the LM head. Anyway, this is just what we said. This is just showing one picture in it. Okay, next. Yeah. Now there are two blocks there. You can see the picture. I'll conceptually try to tell you first, and then we'll get into the blocks themselves and understand how they work. So every transformer blocks consist of two famous pieces, which today have become buzzwords of computer science. Almost everybody who does computer science either swears by them, criticizes them, or just lives with them, whatever it may be. This is where we are today. So okay. So there are two blocks. One is called the attention block or the self-attention block, and the second is called the feed-forward block. Okay. The self-attention block is a very elegant mechanism. I'll soon talk about it. And the feed-forward is your good old neural network, which has been in place for the last thousands of years. No, for the last 3-4 years or more, 6-7 years. Right. So basically the feed-forward network is very simple design. Nothing innovative about it. It has the linearity and non-linearity which you see in any artificial neural network. You create a layer and then you bring in non-linearity, push the linearity into it and produce some output. That is a very straightforward feed-forward network. But there are so many of those. Okay, the self-attention layer is new. Again, attention mechanism was not created by these folks, by the people who wrote this paper, that is Vaswani and team. It came somewhat earlier, but the way they clubbed it was very smart, and this paper became a celebrity paper. Okay. I hope all of you read this paper, because even if only 10 have read, it's important that all of you read before you do anything further in life. Okay. Anyway, we'll now get into each one. So there are two parts: attention layer and the feed forward. Okay. Let's see what each does and how it does. Next. Okay. Okay. Now, conceptually, what does attention do and what does feed forward do? Okay. Now here, see, it is not known honestly what each does. Somehow they get it right. People have tried to postulate why are they getting right after hindsight. That means they got it right first, and then they started figuring out, why are we getting such right answers? So there must be something going on. So whatever I am saying is not proven by maths or proven by anything, it's only conjecture. Conjecture means it's an assumption. So this may be wrong, it may be proven wrong, maybe 2 years later, 5 years later. But as of now, the conjecture of attention layer and feed forward layer is as follows. They say the job of the attention layer is to pay attention to the rest of the sentence. That means, I'll give you examples, but let's say we are using a sentence in which we say the dog ran after the cat and it hid under the table. I'll say this again. The dog ran after the cat and it hid under the table. Now, it here refers to whom? Who said dog? Okay. Normally it refers to the cat. Okay. Now, this is called knowledge, which comes from the inter-word understanding. So, it basically is impacted by what words came earlier. The meaning of it, whether it is cat or it is dog. This is very common. The professor gave an assignment to the student who then decided to get it graded. Now, who refers to the student or to the professor. If you read the whole sentence, obviously it makes sense. But at that point, who basically means the student. So, this obviously is because you have to make a conclusion based on whatever the previous words alone. There is no knowledge other than linguistic knowledge which is involved here. You have to get this. See, it is only language knowledge which says it should be cat and it should not be dog. It is only we are incorporating at that point language knowledge which the system has learnt over time and what tokens have come before this word in this sentence. All that only is determining. So they said attention layer is all about giving importance to the words which came earlier and how those words impact this word and how this word may impact those words. So it's basically an impact analysis of a previous word onto this word and vice versa. This word will also impact those words further. So as of now, I am only understanding what the previous word's information is coming to me that is enhancing my knowledge. As we often take the statement, John took Mary to a restaurant. John took Mary to a restaurant. Okay? And what is the next? Yes? Okay. Yeah, you can make it anything. And he bought her a drink. Okay. This is the sentence I use in my example. So, somebody took somebody, okay, to a restaurant and he bought her a drink. Now, here it's obvious that he means John or whatever and her means Mary. Are we there? So, what happens here, if you realize, if I use he now, okay, if I use he now, the he is the John. Whatever information has come on John so far, whether John is a rich guy, John is a poor guy, John is a bachelor, John is a married person, whatever he is, that all knowledge gets transformed into he or gets transferred to he. Agree? Now, this is only a linguistic transfer. Okay. Now, on the other hand, if the sentence goes something like this, John took Mary to a restaurant, he gave the keys to, good, you read that, to a valet. Yes, he gave the keys to a valet. Now, this knowledge is different. How did it come to know that valet is there in a restaurant? Valet is not there at home. Valet is there in a restaurant. Are you getting me? Now, this is not linguistic knowledge. This came from historical knowledge because so much of knowledge was consumed and somewhere the LLM figured out that restaurants have valets and valets collect the keys and the keys are used to park the car. Are you getting me? This is not coming from that sentence. I hope you are able to make the difference. See, some information about a particular word comes from the previous words. Some information comes because of the historical context of that sentence. How this sentence is used. You need to be able to differentiate between these two. Now, if you differentiate between these two, you will understand where attention mechanism is triggering and where feed forward mechanism is triggering. Now, they say that attention mechanism is responsible for capturing the rest of the information from the word and feed forward is capable of learning over time through the various thousands and millions of documents which have been processed. What has transpired in those million documents, it is consumed all that and learned. Restaurants have valets, valets keep the keys, keep the cars and they want to get keys. This knowledge has come because of that. Now here he gives an example. There is a movie called The Shawshank. What is the next word? Redemption. Now this if I say the Shawshank, full stop, stop. The next word is what? Redemption. Now you tell me, for getting redemption, is attention involved or feed forward involved? It's feed forward. It is because so many knowledge of movies has come that the moment you use the first phrase, you are able to give the second phrase. This is coming out of the feed forward networks. This is coming from knowledge which has been gained. It is not coming from knowledge of linguistics. There is no linguistics involved here. How do you know after this word redemption has to come? That is historical knowledge. That is by memory, by information, and not by linguistic help. Linguistic will not tell you that redemption should come here. It's the name of a movie. How will it come that way? You're with me? So again, I am giving you not so correct, because it's not possible to give a precise definition of what attention does and what feed forward does. But between them, one of them for sure, attention, captures the linguistics, second one captures the knowledge, and together they start lending meaning to the sentence or to the word. Are we clear? So this is at broad the meaning of attention and feed forward. Now we'll go one step further. Okay, so Shawshank Redemption. So now the attention layer. So yeah, can you make it bigger? Left. The sentence now is, this is just to illustrate what I just said. Thoda bada kar. Can you scroll to the left? No. Okay, let's live with this. The sentence at the top is, no, it's okay. The dog chased the squirrel because it. Now, the word it is associated with the squirrel. Now, this is what is from the language itself. This is nothing to do with information. It's the way the language is constructed that it figured out that it refers to squirrel. And that is the job of the attention layer. And the redemption is the job of the feed forward layer in the previous sentence. Okay. So this is only to tell you what purpose attention serves and what purpose feed forward serves. Nagireddy, you'll have to. Next. Yeah. So now you are looking at an attention layer. It can be anywhere. How many attention layers are there? Hundreds. Okay. Each thing is in hundreds. So you are seeing there are positions in the word, and currently we are processing, let's say, the last word at the moment. Let's imagine we are at the last word. Now it is looking at the previous words, but now you'll understand, you just said each word is processed separately. Correct, as of parallelization. But when I am looking at this word, I am looking at all the previous words of the earlier time. So, okay, I am just pointing out, sorry. No, you want just, a laser? No, it doesn't matter. So, that this word which I am pointing to is determined by the previous, these two, these three, four. All of their attention is being captured by that red line, okay, of the previous word, not of the current. Current is still going to get processed parallelly. Of the previous earlier four words, this guy is getting the complete transfer of attention from them, computed in a particular way. And that attention which is coming is influencing that blue bar to become the red bar, which is enriched with context information from other position. Initially, the word did not know about its neighbors or knew little. See, each layer as it goes up learns more and more. So, it knew much little about the rest of the words. When it went through this attention layer, it learned some more about the association with the earlier words. And this goes on layer after layer, and it keeps learning a lot from its neighbors as the sentence goes through the transformer. Okay. So now let's see how does this maths happen next. I hope the maths is next. Okay. Yeah. Now comes two very important pieces. So there are two steps in attention mechanism. One is called, okay, now you will understand those equations well. One is called relevance scoring and the other is called combined scores taken from relevance. I'll again elaborate. Okay. Now you'll have to think with me little deeper. Okay. During attention, every word says, this is who I am. Imagine words talking to each other. So during attention, every word, this word, let's look at this word only. It is telling every other word, this is what I am. I am a pronoun, I am a noun, whatever I am. I am telling this to all the words before me. And what is it trying to say is, how similar are you or how close are you to what I am seeking. So I am announcing myself and also I am saying, this is what I am looking for from you. And it looks at each word and says, I am so and so, just it's introducing itself, and this is what I am seeking. It's like marriage making, right? I am so and so, this is my biodata, and I am seeking this. No, yes. Now, are you with me? Now, all the other words will tell this word, this is what we are, and either we are very similar to you, that means we match you, or we are completely different from you. So this is called relevancy calculation. Okay, now please get this. First, I announce and figure out how relevant is this guy to me. Does he have common interest with me? Or does he or she have common interest with me? Are you with me? Are we having common goals in life? That's being philosophical, but are we similar? And that is called relevance scoring. How close are you to me? Like it is closer to the squirrel, not so close to the dog. So it figures out, okay, I am similar to this guy. And then once I decide how similar I am, the relevance of this is expressed as a score. This is called attention score. So the closer I am to you, our combined attention score will be very high. If I am something different from you, my attention score will be very low. So I have an attention score which defines how relevant the other word is to me, A. B, once I determine relevance, second what I do is, I say how valuable you are. Your value is very less. We may be thinking alike, we may be, our thoughts, our goals, our ambitions may be same, but of what value are you? Are you a valuable person? Do you have a lot of money in your pocket? No. That is called value. So I take all of this and bring it into me. This is what I am learning during attention. Did I sound okay, or you are getting what I am saying? So each word, or especially the word which is getting focused, it is learning how close is it to the other words, and if those words have some value, that value is in proportion transferred to me, not in completely. To what proportion is it transferred to me? To the proportion that we are similar. If we are extremely similar, all your value gets transferred to me. If I am not similar to you, only that very little value of that comes to me. So it's a very, very curious and very amazing instrument by which relevance scoring happens during attention mechanism. But this is what happens. I think this is intuitive to understand, right? Now, once the relevance scoring is done, there is a second scoring called combining information, which is bringing information from all the words, their value, and putting it to me, predicated by how relevant they are to me. Are you with me? Okay. Now I'll just take a step forward and say this in computer science. What does this mean? Okay. Now listen again. There is a famous equation in attention. What is that equation? K Q K T divided by root of the D model into V. So that equation is correct. The equation is this. This is a very famous equation. It should be etched in your mind, believe me. It has more significance today, and I am saying this with full purport and impact, than E is equal to mc squared. You people think E is equal to mc squared changed the world. No. Yes, it did. But after E is equal to mc squared, if any any equation is more important or as important, I would say attention is equal to Q K transpose into V divided by root D model. I'll come to. Is the next most important or as more important? For us as computer science, probably that is more important. Okay. Now let's talk about this equation. Can all of you visualize this equation in your mind? Q KT, KT means K transpose. First let's look at this. Now this part is called relevance scoring, where Q is called query, K is called key. So now I'll try and give you from my analogy the meaning of Q, the meaning of K. Q is what I am looking for. Every word has a Q. Every word has a K. What I can offer. What I am looking for, Q. What I can offer, K. What you can offer and what I am looking for, same, our relevance is very high. Yes? And V, what is your value? You may have a lot of similarity with me, but your value is V. So, first I multiply QKT, I take the transpose of K to adjust the matrices, nothing more. That we do all the time in maths. So, QKT, I multiply Q. Q is my vector, which I produce from my vector for my word, that vector which you see there, bottom. From there Q is produced, K is produced, V is produced. How is it produced? Through learning. The network learns. So each token or each vector has its Q, K, V. You multiply that Q with other guy's K, not by my K, right? Other guy's K, take that combination, it becomes relevance, and then you bring down each guy's value factored with that relevance or measured with that relevance into me and add it up. That is the attention I have. That is the attention I am getting from the rest of the words. Now, surprisingly, this has worked very well. And all of these are learnable matrices. The network is learning for a given word, what should be its Q, what should be its K, what should be its V. It's all learning. It's learning over time. Just like in a CNN network, weights are not known. Similarly, Q, K, V are not known. They are figured out. As the network learns, these weights are figured out. This Q, K, V. When we say in a transformer, those billion parameters, what are they? They are basically these matrices, Q, K, V matrices for each token. Those are the matrices. So those are the words in action. So many vectors are in action. So that is called doing the relevance and then doing the combined scoring. Okay. Okay. Now let's look at the equation here. The inputs to the layer are the vector representation of the current position or token and the vector representation of the previous token. This is used to measure attention. Next. Okay. So for every token, what is generated? A query, key and value. Who generates it? The learning. This is all like weights. These are the parameters of we don't know how much is Q, K, V for any sentence, for any token. It has to be learned. Okay, next. Okay, now the two operations. So you see the position and you see the projection matrices which are created for that particular token. The Q, K, V are created. Now next. Okay, they are created through learning. Okay, so these are the matrices. They are called projection matrices. Next, how do they work? Okay, thoda bada. Yeah. Now, if you notice, for every word, there is all the Q's, K's and V's. I think it's not come out here too clearly. The current token gets multiplied with the, like that, for every token, there is a Q. You see there, in the below picture, there is a Q for every token, previous tokens and the current token, and similarly keys and similarly values. Okay, next. I think this is better to look at it as an equation rather than, it's not always possible to capture it as picture. Okay, this is the attempt. Next. Now this is how it comes. Yeah, this slide may help you a little bit. Okay, can you do better or no? Okay, the sentence is, Sara fed the cat because it. That is a sentence. Now, if you notice, the relevance scores of it with cat is very high. Now, the value which gets transferred is different, but the query is it. We are looking at the word it, let's say, and we are seeing how relevant is it to itself. We don't care. If you see, from it is looking at all the words back. Are you getting me? It is look at it and it is looking at all the words behind it, before it, and trying to determine how much those words are close to me. That is relevance. So it discovers through linguistic enabling or learning that it is closest to cat. That is how it decides that value of cat or attributes of cat have to come to it. So whatever sins or whatever good things which the cat has committed in the past, all of them come to it. Why? Because it relevance to cat is very high. The relevance score you can see there, the cat is 50% and all the others are low. Again, everything gets computed, but you see the maximum score for it comes from cat. So cat's attributes come and flow into it in a very high value. Is this clear? Yes. Okay. So this is what attention mechanism works. Okay. Next. It's called transfer of attention. I think somewhere you will have the equation. Okay. And then there is the, I think, the feed forward story which happens, which is not, and then combining the information. I think the equation is shown somewhere or no? This is same. Recent improvements we don't want to see. Go ahead. Oh, sorry. Go back. Go back. Now those are the values. Can you make it bigger? Okay. Now if you notice, the values are getting transferred. This is the attention mechanism in action. So if you see it is cat value, you see is the highest. The second highest value is the, and if you see the values of each one of them are given, but the two values which will have maximum impact on the value which comes to it are going to come from cat and the. The word cat and the word the brings in the most highest value into it. Okay. Now this is attention mechanism. Now feed forward mechanism I just described to you is very simple, very trivial. It is basically a very simple network. I don't know whether it is shown here. Go next. This is the key value combination, and the feed forward, go ahead. No, this is not, no. Okay, no, it's not here. Okay, this book goes now somewhere else. I'll just tell you what is the feed forward. Feed forward is a basic network. See, the output for every token is a vector we talked about. So, what does the feed forward network do? What is the size of every vector? D. That is where the root D model comes. That is a size, that 1024 or 8192, that is a root D or D. So, that size of each token as it moves through the network is D. And what it does in feed forward is, it transforms D to 4D and then brings it back to D, and during this process it learns a lot because there are so many parameters, simple weights involved in transforming D to a bigger dimension so that its knowledge grows, and after that it again condenses it. So that's how D expands in knowledge and shrinks back into same form. So it accumulates knowledge and then shrinks back. So that is how feed forward works. It's a very simple network. And then there are normalization layers in between. Okay. So this is in short transformer. Okay. Now I have not gone into too much detail because it needs one more session, just looking at time and looking at your faces. So it's about, normally this thing cannot go beyond 1.5 hours. So now there is also code which I want to illustrate. But I am sure you will agree with me that now is not the time to talk about code. Code is very involved and we will go through each line of that code to understand just how this happens. The process is, again I am summarizing: input, tokenized, becomes tokens, tokens transform to vectors, embedded vectors using embedding. Each token is taken, all the sentence consists of multiple vectors, each token becomes a vector. So multiple vectors simultaneously go through the network. The network consists of two blocks, attention and feed forward. Attention learns from the linguistics, feed forward learns from the history of the text. Together they learn and they generate output tokens or output vectors. We don't use earlier vectors, we use only the last vector. Based on the last vector, the LM head generates a probability distribution, and we take the highest word of that probability and generate the next word. This is the process. Now I know some of it will be clear, some of it will not be clear. That's the intention. So it will take another session. Okay. Now this book, as I already told you, is J. Alamar. This is a very good book. Go through it. I am on chapter 3. I have skipped the embeddings chapter because I thought embedding is conceptual. And if you want to read up on embedding, that is there in the chapter. But tomorrow I will not be talking about embedding. I will be focusing on the transformer block. That is how attention is programmed, how feed forward is programmed, how the normalization is done. We will use embedding of course, but we will see it only as a black box.